You get me the credit on that one? You said it was right when we went over the.
Oh, that's right.
Can we do that?
No. I forgot about that.
I can meet.
Yeah. Shoot. Okay. Because everybody's just going to get 4 points for that. Did I hit recording? Are we recording? Yeah. All right. So chapter 11, we're now on to gases. So we've moved on from geometries, bonding, that kind of thing. This is sort of a shift in the same way that when you guys were talking about like electrons and electromagnetic radiation, and then the way that, you know, I guess that led into bonding. Yeah, I'm trying to develop this sort of overview of chemistry because there are these things that sort of build up onto each other, but they only build into sort of stacks. There's some bridges that connect them between, like we'll see with some of the stuff for gases. It lets us figure out, these rules for gases let us figure out how many moles of a gas we have if we're given a volume, or how much that volume of gas weighs at different temperatures and pressures. But currently at this point, we've got sort of electronic configuration, bonding, then there's stoichiometry, which is like particularly working with reactions. And then there's now gases. And so we're going to start, we're going to build sort of this new tower of concepts from the ground up. And this all is really based on kinetic molecular theory. So if you can really get this kinetic molecular theory down, that's kind of small, huh? I don't know how to zoom, so it's not just my desktop background. Don't worry about if you can really understand these principles, everything else makes sense out of these. So this explains everything, but we'll talk about the more general rules. So a gas consists of small particles. The particles of gas are usually very small. And actually, we talk about them as if they don't exist at all. No attraction between the particles. And then the actual volume occupied by gas molecules is extremely small compared to the volume that the gas occupies, which is sort of a fancier way to say that there's a ton of space in between the individual atoms and molecules. And that's part of why they don't interact with each other, because they're too far apart. Then number 4, gas particles are in constant motion. Oh, it does say it. Moving rapidly in straight paths. So they all start out moving randomly in random directions. They move in straight lines. They never stop moving. And then the average kinetic energy of gas molecules is proportional to the Kelvin temperature. And that's going to be sort of a consistent theme throughout this chapter, that we need to be working in kelvins. As we'll see later, Kelvin is related to absolute zero. And so when you start from there, it simplifies a lot of other things. And some of these laws don't work if you're in Celsius versus Kelvin. Oh, there was one more thing that I wanted to add here. Right, so when I think this is part of it. Every time they hit the walls of the container, they exert pressure. And an increase in the number or force of collisions against the walls of the container can cause an increase in pressure of the gas. It doesn't say it in here. But when these particles interact with other stuff, we assume they do it completely elastically. So like billiard balls on a table, all of the energy is transferred. Well, not transferred. All the energy is bounced back off of whatever they interact with. So they do run into each other. They bounce off elastically. If they hit the walls, they bounce off elastically. And so we're going to focus primarily on these 4. Well, this gets cut off because it's on the other side. But pressure, volume, temperature, and the amount of moles or the number of particles. Pressure, volume, temperature, the amount of moles. So those are the 4 properties that we're going to use to describe the gases and to describe how they change. Because as we start to play with these sort of different sliders, they have effect on the other sliders, on the other properties. Zoom, please. Thank you. Today's simulation was for, I think it's a bonding simulation, right? I don't remember. I looked at it briefly. Okay. So I think you probably have covered this. This is going back to stuff before I started teaching you guys. But our different sort of phases have different properties. Solids hold their shape and they have a fixed volume. And we know this, or well, this is the case because the atoms and molecules are so close to each other and they're not allowed to move around each other because they're blocked by other particles. Liquids are also completely packed up against each other, but they're no longer held in place by the molecules around them. So they're able to slip and slide around. And that gives us a fixed volume, but they don't have a fixed shape. So they'll sort of fill the container with as much volume as they can, but not go any farther than that. Gases, like we just talked about, they're really far apart. They're not tied together at all. They will fill the shape and the volume of their container. This is like when somebody's cooking at one end of your house or apartment, and they throw some garlic on the stove. That smell is a gas, and so that's going to pick up and then immediately start spreading in random directions until it fills your entire house or apartment. They just keep going. So to make sure that we understand these different units that we're going to be working with, we have pressure, which is the force exerted by a gas against the walls of the container. So that's the one that's, you can think of, trying to think of like an analogy, but it really is just you have the wall of a container. The pressure is related to the amount of particles that are hitting it per second and how hard they hit it per second. The volume, that's the space occupied by the gas. Usually we're going to talk about that in like terms of a cylinder or in terms of like a balloon, right? That we have a sort of fixed or set volume. That's going to be in liters or milliliters. Hopefully we'll talk more about these. So atmospheres, millimeters of mercury. Actually, there's a slide on that. Torr and Pascal for pressure. For temperature, again, it has degree C in here, and you can use that sometimes, but you have to know when you can and when you can't use it. You can always use Kelvin. So if you convert from degree C to Kelvin, you're just kind of safe in every situation. So temperature determines how hard those particles or how fast the particles are hitting the wall, so that's related to pressure. The amount of particles, which we're going to talk about primarily in moles, you might get a question, at least in the homework, about the grams and then having to convert from grams to moles of a gas. The calculations we're going to do are going to use moles. And that's the quantity of gas present in a container. So if you add more moles to a container, that's a fixed size. You're going to have more pressure because you have more particles that are impacting the walls. So atoms or molecules are attracted to each other to some extent. When we add thermal energy, we can turn a solid into a liquid, liquid into a gas. And then once we've gotten to gas, basically all of the energy that we've added has gone into breaking those bonds to separate the atoms and molecules from each other so that they have no attraction because they're moving too fast to stick. Gases are mostly empty space. Yeah, it's easy to, so yeah, gas atoms, molecules are relatively far apart. We don't think about this day to day, that the air like in this room has a mass. It's probably more than you would expect, but it's also not that much. In fact, atmospheric pressure, so like at sea level, is like 14.7 pounds per square inch. That's because there's that mass of air above you. So for every square inch, there's 14.7 pounds of air between you and space. So because there's a lot of space, we can compress them. And we can compress them because there's a lot of space that they can squish together. Pressures are force per unit area. So like I was saying, the one that we're probably most familiar with is PSI, which is, well, pounds per inch squared, pounds per square inch. And something like so that's related to area. So in your bike tires, they have to hold up less weight than a car, but since the bike tires are so skinny, they're usually pumped up to a pressure of 65 all the way up to, if you've got really skinny road bike tires, like 120 PSI. Whereas on your car tires are usually at a pressure of 30 PSI. And that's because the skinny road bike tire is making just this really, really thin contact, maybe even less than a square inch, but that small area has to support your whole weight. The car's a lot heavier, but you might have as much as like a square foot. So 12 square inches, so 12 square inches contacting the ground. And each of those square inches is holding up 30 pounds, or is able to hold up 30 pounds. So you could do 12 times 30 and get that a single tire could hold something like 360 pounds each, which is probably a low estimate, honestly. So for example, if you blow up a balloon, you put more pressure inside the balloon than atmospheric pressure. So the difference in force between you blowing into it and then the pressure forcing the air back down, the balloon expands, and the balloon expands to the point where the pressure inside is equal to the pressure outside. Now, if you open that up, the elastic of the balloon is going to cause it to blow all of that air out. Right, so atmospheric pressure is all of this gas pushing down on you. So barometer looks like this. You fill a long tube with pure dry mercury. You fill that tube completely. There's no air inside of it. And you take that thing and you cover up the end and you put it into a bath of mercury like this. This mercury will fall and leave a perfect vacuum or nearly perfect vacuum above that mercury. And this amount of vacuum is related to the amount of pressure outside of the tube. This is also related to, in my slides for my other class, talk about if you wanted to make like a really, really long straw, there's a limit to how tall your straw can be. It's about 10 meters if you have a perfect straw, perfectly rigid walls, that's not going to collapse. And that height, you can only go up to 10.4 meters because once you have a perfect vacuum, what's actually happening is you run out of air pressure on the outside to push the liquid up that straw. And that height of that straw is going to be, well, if you had a huge 1-inch straw, this was 1 inch square, you could have 14.7 pounds of water in that straw. And that would be as tall as you could make it. Because it's all about the amount of pressure forcing down on the outside to keep this mercury up. So the reason you use mercury for a barometer, actually, there's a question. Why do you use mercury for a barometer and not water? Mercury is really dense. So this much mercury also weighs, it's not going to be, I mean, if this is 1 inch or 1 square inch, this would be 14.7 pounds of mercury. I think the density of mercury is like 13 or something. So it's really, really high for a liquid. So if we made this out of water, this would have to be over 10 meters tall in order to get a measurement. But here it's just 760 millimeters, which is still almost 2/3 of, or 3/4 of a meter. Right, so our mercury pressure, because these are Mr. G's slides, I don't know what he's asking for here. If the tube is longer than 760 millimeters of mercury, it drops to a point at which the column of mercury in the tube is supported by just the pressure of the atmosphere. Yeah. So the mercury pressure would be, and actually it's the base pressure that we use for most of our calculations, which is going to be 1 atmosphere. So 1 atmosphere is like standard pressure for Earth, because that's the pressure at sea level, average pressure at sea level. So standard atmospheric pressure is 1 atmosphere, which is also the exact pressure exerted by a column of mercury 760 millimeters high. So that's from the top of the pool to the top of your column of mercury. Normal pressure of the atmosphere at sea level, torr, is equivalent to millimeters of mercury. Now that I think about it, I should know the origins of that, but I do not. So might be interesting to look up. The SI unit, though, for pressure is the Pascal, because the Pascal is defined as a Newton per meter squared. So based on other SI units, you get the SI unit, which is the Pascal, which is actually a very, very tiny amount. So to equal 1 atmosphere, you have to have 101,325 pascals. So more commonly, what you'll see is 101.325 kilopascals. All right, so using SI units to make it 1,000 to get it sort of in numbers that are more reasonable. You can also use inches of mercury, centimeters of mercury, or millibar, or pounds per square inch, like we talked about with car tires. It says all of the above values of these units are equivalent to 1 atmosphere, at least for the ones that are given, right? So these are 1 atmosphere. This is 1 atmosphere. I would bet that your book has oh, never mind. See next slide for summary table. I would bet your book has a table like this, where it's going to show you, right? So Pascal, and this is in scientific notation, but kilopascal, all of these things are 1 atmosphere. And so you can convert from this to atmospheres, or you could convert, we're just doing atmospheres to there. You could make another conversion factor out of this. So instead of say going from, I'm not gonna use pascals. Let's say we wanna go 760 torr, and we wanna go to PSI. Since 760 torr is equal to 1 atmosphere, and 14.7 PSI is also equal to 1 atmosphere, then we could say 760 torr is equal to 14.7 PSI. Now, that being said, we're primarily going to be using atmospheres. If you did need to convert between these, you can create another conversion factor using this common value of 1 atmosphere. So if we wanted to do these questions here, so we have 1.2 atmospheres, standard unit conversion problem. We'll just look on this table for our conversion between atmospheres and PSI, because the units we're given are atmospheres, and we want to go to PSI. So we're going to multiply this by our conversion factor, and we want to cancel out atmospheres. So it's 1 atmosphere there, and then 14.7 PSI. And then when we multiply these and then divide by atmospheres, we'll get calculator. $17.6 Well, actually, we only have 2 sig figs, but psi. So with correct sig figs, you'd have 18 psi. So these are just unit conversions. 31.1 inches of mercury. And we want to convert to atmospheres. So we'll look on our table for inches of mercury and atmospheres. So now because we have inches of mercury, we want to get rid of those units, put inches of mercury in the denominator, so 29.9. And then in our numerator, we'll have 1 atmosphere. 31.1 divided by 29.9. And that's going to be 1.04 atmospheres. Oh, it's cold in here. Any questions about that? Conversions? Cool. So pressure is dependent on the number of moles and the temperature. Pressure is produced by gas molecules colliding with the walls of a container. So at constant temperature and volume, the number of collision depends on the number of gas molecules present. So if they're all moving at the same speed within a container, it's just dependent on the number of gas molecules present. If we add more molecules in there, we're going to have more collisions, and we're going to have more pressure, even though they're all moving at the same speed that they were before, and at the same distance, actually, too, to travel between one side of the container to another. It's kind of like the bouncing DVD logo, just waiting for it to hit a corner. It's going to be bouncing around this in 3 dimensions, or each of the molecules is. So the number of collisions can be increased by increasing the number of gas molecules present. And if we double the number of molecules, the frequency of collisions and the pressure should double for an ideal gas. All right, so if we have, 1 collision per second, all of a sudden we add twice as many atoms, and then we have 2 collisions per second, that's double the pressure. A lot of these are, actually all of these, if you're just changing a single variable, it's easy proportions. So like here, if we double our particles, double the pressure. If we cut the number of particles in half, we also cut our pressure in half. So that's a directly proportional relationship. So when the temperature, mass, and volume are constant, the pressure is directly proportional to the number of moles or the molecules of gas present. The pressure of a gas in a fixed volume increases with increasing temperature. The increased pressure is due to more frequent and more energetic collisions of the gas molecules with the walls in the container at the higher temperature. So they're just, temperature, very literally is the average kinetic energy of the particles in the container. And so if we increase that kinetic energy, we actually increase the speed of the particles. This is actually, well, I guess it's a Chem 1 thing. The reason that we're running out of helium is because it's the average speed. So if you were to plot out the speed of all the helium molecules in the atmosphere, there's this curve that looks kind of like that. So this is increasing speed. This is like the number of helium atoms at that speed. And this just happens to cross over with escape velocity. Escape velocity is the speed that you need to get to leave Earth and escape Earth's gravity. And so there's some proportion of helium that's always just leaving Earth because it's fast enough. It's a small proportion, but so when we're increasing the temperature, we're actually taking this curve and we're shifting it to the right because we have more particles moving faster or more particles moving slower. And that has an effect on our pressure. So here, actually, this is a really good example of why we need to use Kelvin, because this is in degrees C. So if we really can quickly convert this, that's big enough. this is 0 degrees C is 273.15 Kelvin. 100 degrees C, I can do that math, 373.15 Kelvin. So when you look at this and you see it going from 0 to 100 real quick, it seems like it should be like, because we have 0 starting out, we're going up to 100, it should be infinitely more pressure. But in reality, we're increasing by a factor of about a third. And so our pressure also increases by a factor of about a third. So if you're looking at absolute temperatures in Kelvin, if we went from 273 to 2 times 273, then our pressure would also double in a fixed volume container. Does that make sense? All right, so at constant temperature, the volume of fixed mass of a gas is inversely proportional to pressure. So, yeah. So this is one of the cases, right? So the temperature here, we're not changing temperature. Constant temperature, let me highlight these things are red. So you have constant temperature, constant volume, like fixed mass. So, right, same number of moles. So the only thing that we change, if we were to do an experiment to see this, would be inversely proportional, right? Yes. So we would just be changing volume and observing what happens to the pressure, or we would change pressure and observe what happens to the volume. So this is like if we took, say we have a box. We've got some number of particles in here, a certain temperature. If we could magically make this box twice as big, doesn't matter if it's the dimensions. Now we have the same number of particles in here, but they're way more spread apart. So our volume increases, our pressure drops. Because now these same particles, they have more room. So the collisions are less frequent because it takes a particle longer to travel from one side to another and then back again. So there's more room to move around in. So to do this, it's easier to show a change in volume than it is to show a change in pressure. Yeah, the only really good way to do this. So if you're looking at two different states, the equation that we use is, actually I think it's usually written P1 V1 equals P2 V2. And the way questions for this kind of problem will be given is you'll be given at least 2 different pressures and then 1 volume, or you'll be given 2 different volumes and 1 pressure. So you'll only ever have 1 variable that's not filled, and so you can always rearrange to solve for the one that's missing. So that's for Boyle's law, that's the equation to memorize. Oh, and actually, let me take a half step back here and talk about this, right? In terms of kinetic molecular theory, our pressure is determined by the number of particles, or the frequency of collisions and the speed of those collisions. So that's why increasing volume, we're decreasing the frequency of the collisions, and that happens to be exactly proportional. So kinetic molecular theory, again, is the root of all of these things. So again, we have constant temperature, volume, fixed mass, inversely proportional to the pressure. So V 1 over P. So for example, the pressure of a gas is 1 atmosphere, and the volume is 1 liter. What is the new pressure when we decrease the volume by half? So these word problems can be really easy because all you have to do is write down all of the numbers that you're given and then look for the equation that you can slot all but one of those into. So I'll show you what I mean. So we're given a pressure. So I'll just write down pressure is equal to 1 atmosphere. I'm gonna call this P1 because this is our sort of starting condition. And our volume, our V1, is equal to 1 liter. And it says, what is the new pressure? Okay, so we don't know that pressure. So P2 is gonna be our question mark. And it wants to know what happens when we decrease the volume by 1/2. So this is probably one of the slightly trickier ways to write this. Because now our V1, or V2, excuse me, is going to be half of V1. It's going to be 0.5 liters. Now at this point, we only have one equation. P1 V1 equals P2 V2. But there are at least, well, depends on this book, 2 or 3 or 1 or 2 more equations that we're going to cover that are these simple gas laws. So now we can slot these in. We've got P1, we've got V1. So I'll put those in there. So 1 atmosphere times 1 liter is equal to our P2, which is our question mark. So I'm just going to write P2 times our new volume of 0.5 liters. And now we've got all the numbers filled in except for a single variable. And now we can just rearrange this to solve for that. And I want to highlight here too, if we multiply 1 atmosphere by 1 liter, our units are going to be 1 atmosphere liter. Okay. So then if we go here and we have now P2 on this side times 0.5 liters. So we're going to divide both sides now by our 0.5 liters. Because this is another way that you can solve these without memorizing the equation necessarily, is that when we do this, we now have atmosphere liters, which is a weird unit, but we're dividing by liters. So when you divide something by itself, it's 1, so our liters cancel. And so our final atmosphere will be 1 atmosphere, well, it's 1 atmosphere liter divided by 0.5. And when you divide by 0.5, you multiply by 2, but you can just type it in your calculator. We'll get 2 atmospheres as pressure 2. So to go back to, right, this law is that pressure and volume are inversely proportional. We shrunk our box by half, so pressure has to increase by double. Wait for the writing. I will post these. Also, if I don't post something and I say I'm going to post something, please remind me. I try not to forget these things, but I do. I won't be offended if you remind me. I was aiming for like 2:25. Yeah, 2:25, because that would be like our regular lecture that we would have had yesterday morning. And then we can work on lab if people want to stay and work on the lab, which is a simulation. Okay, so what volume will 2.5 liters of gas occupy if the pressure is changed from 760 millimeters of mercury to 630 millimeters of mercury? And again, the strategy for all of these gas law problems is just start writing down what you're given in the question. So, oops, you can do this just as you're reading it. So we're given 2.5 liters, which is the volume. So V1 is going to be 2.50 liters. Oops, not V2. If the pressure is changed from 760 millimeters of mercury, so our pressure 1 is going to be 760. Yep. So P2 is then going to be our second pressure here, 630. And then this one's not written out as straightforward as the last one was, but I guess I should have written this first, is what volume will we get? right? So at the end, our V2 is what we're looking for. So again, if we look at our equation, P1 V1 equals P2 V2. We now have at least 3 of the numbers to fill in there to solve for the last one. Really the only unit too, so you might see here that we have millimeters of mercury instead of atmospheres. All measures of pressure are absolute. So you go down to 0 pressure and that is 0 pressure, unlike degrees Celsius or Fahrenheit, where 0 is just like an arbitrary number that we picked. For degrees Celsius, it's water freezing. For Fahrenheit, I actually have no idea what it is for Fahrenheit, why 0 is what it is for Fahrenheit, because water freezes at 32. So P1, 760, our V1 is going to be 2.50 liters, and our P2 is going to be 630 millimeters of mercury. V2, again, what we're looking for. So we'll do 760 times 2.5. We'll get 1900 exactly. I like that. Again, this is going to be millimeters of mercury, liters. I do recommend, like every opportunity, write out all the units. It takes a long time and you're going to use more paper, but in the end, you'll be able to see what you did later if you try to come back. And then we're going to divide both of these sides by 630 millimeters of mercury. So we'll take our 1900 divided by 630, 3.02, just rounding up there to 3 sig figs. And then our millimeters of mercury cancel. So we get liters as our remaining unit. And then you can sort of double check your work here, because we know that if we are decreasing the pressure, then we have to increase volume, inversely proportional. So we do indeed go from 2.5 liters and our volume increases to 3.02 liters. Units of volume are also like pressure, absolute. If you have zero liters, that is 0 liters, right? No volume. So that again, the only units you need to worry about are temperature in terms of converting, as long as you're going to and from the same. So use the same strategy here, right? A gas occupies a volume. All right, we got a volume of 200 milliliters. This will be our V1 at 400 torr. So that's our P1. Actually, important to note here, there is a decimal, which means that we have 3 sig figs for each of those. And see, oh, these have them up here too. So these are each 3 sig figs because we have a trailing 0, but we have a decimal place. All right, to what pressure? Oh, that's P2. That's going to be our question mark, right? That's our question. Should the gas be subjected in order to change the volume to 75 milliliters? So V2 equals 75 mils. And again, it's just the same equation. So we're going to do 400 torr times 200 mils. That's our P1 and our V1 equals 400 torr and, oops, wait. Nope, not 400 torr, sorry. 75 mils. And then P2 is what we're looking for. So 400 times 200, and then divided by 75 will give us 1,000. Oh wait, we have, all right, so the number from the calculator 1066.0 6 repeating. Huh? So it's going to be in scientific notation. So 1.07 times 10 to the 3 torr is equal to P2. So again, just a quick check at the end. We want to decrease our volume. So that means we need to increase pressure. So we can look at our pressures and say we went from 400, we went up to 1,066. So our pressure increased, everything makes sense. Which means you probably have the right answer unless you type the wrong numbers in. Does happen. Any questions on those? Build in the stack. So this is the beginning. It'll get more complicated when we get to the complete gas law, the ideal gas law. All right, so we were looking at pressure and volume. Now we're going to change gears and see what happens when we start changing temperature and volume. How do they affect each other? Again, this is going to be at constant pressure and fixed mass. So now we fixed our pressure, it's going to be the same from start to finish, and our mass is going to be the same start to finish. Actually, when you see mass here, read fixed moles. Right? The number of gas particles is the same. And yeah, so the volume, I'm going to simplify this. Volume is directly proportional that's an L, to the absolute pressure, or absolute temperature, sorry. Volume, absolute temperature. So this is where we need to be using kelvins. So when we're looking at pressure and volume, those are inversely proportional. So if one goes up, the other has to go down. Directly proportional means that if we increase volume, we have to increase temperature. Or if we decrease temperature, then we decrease volume. And actually, this is an experiment you can do at home. If you take a balloon and you blow it up, it'll be a certain size. If you take it and put it in the freezer especially, and then pull it out later, it will shrink. And if you put it into liquid nitrogen, there's a cool video that I keep meaning to share, but forget, it really shrinks because liquid nitrogen is quite cold. So this is our equation then for volume and temperature. So of V1, T1, an initial set of conditions, and then V2 and T2, an ending set of conditions. So always converting to Kelvin for these. Oh. Anyway, this is Charles' law. Mm-hmm. Pressure and volume is Boyle's law. This is Charles' law. Now, it looks like we'll get through about half of these. We'll finish the rest tomorrow. So absolute temperature, we have to convert. Oh, that's my research advisor. I will call him back. So Charles, of Charles' law, is the guy who did these experiments. And he took his graph because most things down at temperatures this low are not going to be gases anymore. But he did his experiments up here. And then he drew this straight line. So if you have something that's directly proportional, the relationship between them will be a straight line. He said, what if I go backwards? So if you project this line backwards, it intersects the x-axis with negative 273.15 Kelvin, or sorry, degrees C, or 0 Kelvin. And that's why we need to use absolute temperature, because if we don't do this, then we intersect. It intersects in a weird way with negative 273. Yeah. So this is why you need to use Kelvin. And actually, we could do a problem. Might do one later. All right, so we have 3 liters of hydrogen at negative 20 degrees C. And again, gas law problem, we can just go through and write these units down or these numbers down as we get them and assign them to temperature, pressure, volume, and later on, moles. So 3 liters. So volume 1 is going to be 3.00 liters of hydrogen at negative 20 degrees C. So that's our temperature 1. Are allowed to warm to a room temperature of 27 degrees C. So T2. What is the volume at room temperature if the pressure remains constant? And that is a key here. So V2 is what we're going to be looking for. So just like we did with Boyle's law, we just plug these in. 3.00 liters over negative, oh, right. First, we need to convert to Kelvin. So to convert to Kelvin, we just add 273.15. Well, this will be 253.15 Kelvin. And then for our T2, we're going to have 300.15 Kelvin. And then our volume, V2, is what we're looking for. So we can do our 3 liters. We'll do this side first. We'll do 3 liters divided by 253.15. Oops. And we'll get 0.01185. This is going to be liters per Kelvin. And then we're going to have V2 over 300.15 Kelvin. And then we're multiplying both sides by 300.15 Kelvin times 300.15 Kelvin. So when we do multiply these, Kelvin, whoops. Switch the pen. All right, Kelvin will cancel out and we'll be left with liters, which is what we're looking for. So we'll multiply by 300.15. So we get, we had 2 sig figs. So you get 3.6 liters equals our volume 2. And again, we can check our math because we know that volume and temperature should be proportional. So if we've gone from, or if we've increased our temperature, right, from negative 20 to 27, then we should see a proportional increase in volume. And we do. The key is too that the increase from 253, I didn't write them down there, 253 Kelvin to 300 Kelvin is a much smaller proportional increase than going from negative 20 to 27. Even though the absolute difference between them is the same, the proportion is smaller. Actually, just real quick, let's say that we started at 0 degrees C. So instead of this being 3 liters at negative 20, if we do this in degrees Celsius without converting, we end up with 3.00 liters over 0 degrees C. And you can't divide by 0. This is the one really glaring mistake that can happen, is you'll run into this. But if you don't have 0 as one of these numbers, you could do this as negative 20 and V2 over 27. And you'll be able to type all that into your calculator and get a number, but you're going to end up with a negative volume. So even though it looks like it works out, you might be tempted to just, oh, I'm just going to flip the sign. It'll be fine. It's not going to be fine because you'll lose those points. So don't do this. Do you need more time? Yeah. Yeah. Oh. Well, because -20 has two significant figures. So really, when you're doing any calculations, you keep all of your digits and you don't round until the very end. Because that's how you get rounding error. Because at every step you round a little bit, you'll end up with numbers that are significantly off sometimes. Correct. But this is only worth 2 sig figs because we started with 2 sig figs. So one of the ways you can do this to try and keep track of those sig figs when you do longer calculations like this, I like to underline sort of the lowest number of sig figs that we have. And actually, when we add these two together, we get 3 sig figs, I suppose, because it's an addition, so you're keeping the smallest number of decimal places. Maybe it is 3 sig figs. Because this is worth 3 sig figs, and then this is going to be worth the same number of sig figs. So then I underline like here and here. And then it's all multiplication and division after that. So yeah, 3 sig figs.
Start by multiplying both by 3 or dividing by 4.
So I did this first. Yeah, so this is the left side of this. This is V1 and T1. Yeah. So because we have 2 numbers here, I'm just going to divide those. Yeah, so then, yeah, then this cancels out this. And that's how we move it to the other side. So this would actually be 3.56 liters. Yeah. Does that make sense? Love questions. Yes. And actually, in general, for gas law problems, just always use Kelvin. I think for gas laws, you have to. The one that you don't have to do is for the heat capacity equation, because you're using the difference between 2 temperatures. So it doesn't matter if you use Kelvin, but if you always use Kelvin, you'll never be wrong. Unless I ask for the answer in degree C. So we'll do, wait, what did I say? This starts 110, so 25. Okay, we'll get through a little more. So if we have 20 liters of oxygen are cooled from 100 degrees C down to 0 degrees C, what is the new volume? And again, we can go through here and we'll just say V1, because we're given a volume, is 20.0 liters. And then we get T1 as 100 degrees C. And then we're given T2, 0 degrees C. And what is the new volume? V2 as our question mark. So we can convert these first by adding 273.15. So we'll get 373.15 Kelvin. And then we'll get, wait. Sorry, I was thinking about sig figs. 273.15. Because this is an exact number, but the smaller number of sig figs comes from here. So then if we want to keep track of these, we do have 100 with a decimal place. That's 3 sig figs. This has a decimal place as well, so it's 1 sig fig. But when we do addition, we're keeping, again, the smallest number of decimal places. So those actually become 3 sig figs, which makes me a little bit uncomfortable. Okay. What is going on? Okay. So yeah, our equation is V1 over T1 equals V2 over T2. So we just start plugging numbers in. 20.0 liters over 373.15 Kelvin. And then our V2 is our question mark. Don't know what that one's going to be. And then over 273.15 Kelvin. And again, if we had used degree C, we'd be dividing by 0. Right, and so now I'm going to do this side, 20 divided by 373.15 to get 0.05359. Again, you don't really want to round there, but we'll round later. If you wanted to, you could keep track of, this was 3 sig figs. So both of those are 3 sig figs. So here we have 3 sig figs. So I'm using this line underneath the 5 to just indicate if we were going to round this number to 3 sig figs, that's where we would do it. 273.15 Kelvin. And again, this one should have a line under it too. So now we're going to take this 0.053598, which I'm not rounding in my calculator. We're going to multiply by 273.15 to get 14 point, again, 3 sig figs, 14.6 liters for volume. And I did that thing where I was saying you should always write down what your units are, but I didn't write down what my units are. This is liters per Kelvin. Yeah. Oh, that's fine. I'll post the video later.
Yeah, okay. That and the lab, website.
It should, oh, it's in the lab manual. So like the stuff to do is in the lab manual, and then the link should be there too. That's on the syllabus. I don't remember off the top of my head. All right, or tomorrow. Yeah. Okay. So that's that. That would be our answer. Any questions? Yeah. All right. So we can also talk about the relationship between temperature and pressure, or Gay-Lussac's law. So if we could observe the molecules of a gas as the temperature rises, we would notice that they move faster and they hit the sides of the container more often and with greater force. This relationship is Gay-Lussac's law. So we have another proportional relationship. I'll write this bigger. P1 over T1 equals P2 over T2. And like all of the other equations that we've been talking about, we're changing either pressure or temperature, but our volume remains constant and our number of moles remains constant. And our, sorry, I said volume already. Volume and number of moles both remain constant. Oh, actually, I forgot to tie this one back to, where's the first slide? Kinetic molecular theory, right? So if we increase the temperature and our pressure remains constant to keep constant pressure. So if we have our gases in our balloon, we heat those up, then there's going to be higher pressure inside that balloon. But we know we can decrease the pressure by increasing the volume. So that's why to keep the same amount of pressure, we increase the volume as we increase temperature. So all comes back to kinetic molecular theory. There's the practical equations for it. For Gay-Lussac's law, now we've got that fixed container. We're heating it up. We have more collisions and more frequent and more energy in those collisions. So we're keeping it the same size, the pressure increases. And actually, a lot of these relate back to, if you want to look it up, well, you'll probably have to ask me later, the Carnot cycle. So as we increase temperature, the pressure increases. So we go from 200 to 400 here. Again, Kelvin. I guess gasoline engines aren't exactly ideal conditions, but that's a lot of the concepts there are that when you inject gasoline into your cylinder, there's a piston, and then it's ignited. And so not only are you increasing the temperature, which increases the pressure, but you're also increasing the number of moles of gas because you're taking that carbon molecule or the mostly octane, taking that octane and breaking it apart into a lot of other molecules. So you get this rapid expansion because of the temperature increase and the number of moles increases. So that's what causes, that's how your car drives and generates propulsion. Tiny explosions, not so tiny explosions. Okay, so Gay-Lussac's law, relationship between pressure and temperature. Oh, okay, then we jump straight into the combined gas law. So this is definitely something to memorize. Standard temperature and pressure, STP, is 273.15 Kelvin, not degrees Kelvin, just Kelvin, 1 atmosphere. So there'll be a lot of stuff where it's, oh, you've got a balloon at STP and it's heated up to 100 degrees Celsius at the same pressure. How big is the balloon? You know, that kind of question. So we can combine all of these equations though. Okay, so when temperature and pressure change at the same time, the new volume may be calculated by expressing them as a single equation, PV over T equals K. Oh, I see. And for initial and final conditions, which we use the most, this equation looks a lot like the combination of the ones we had before, P1, V1 over T1 equals P2, V2 over T2. So just Boyle's law was P1, V1, P2, V2. Then we had, was it Charles' law, which is just volume and temperature. And again, in those, we kept pressure constant, so we can leave that out. If pressure is the same here and the same here, doesn't matter. Then in Gay-Lussac's law, we have pressure and temperature with a constant volume. So we've just taken all of these and combined them together. Hence the combined gas law. So now we could measure, or we could determine our either pressure, volume, and temperature if we changed the other two at the same time. We don't have to go from just one pressure to another pressure and figure out the volume. We can do pressure and temperature and figure out volume, or pressure and volume and figure out the temperature. All right, so if we have, and again, this is like we were talking about earlier, or like I've been saying for all of these, we'll just write down all the things that we're given and then figure out which equation we need to use afterwards. So V1 is 20.0 liters, right? Given 20 liters of ammonia gas, we have T1 at 5 degrees C and 730 torr. So that'll be our P1. We want to calculate the volume, okay? So our V2 at 50 degrees C, T2, and 800 torr. You have to be, like we've seen, I think we've seen a little bit of this in the other questions. You have to be a little bit careful that you're matching up the right numbers with your initial state and then with afterwards in your changed state, right? That relate these. That's why these are all V1, or these are all 1, and these are all 2. So our equation then is P1 V1 over T1 equals P2 V2 over T2. Right, and then again, the reason we're using this equation is because we were given all of these variables. Now, if we looked at this and we saw that maybe our pressure doesn't change between one and the other, then we can leave that off and just use the equation that's related with just those variables. But because we're given a change in temperature and pressure, and we want to calculate volume, we need to use the combined gas law. So let's start plugging these in. Or actually, sorry, before we plug these in, let's calculate. This is going to be plus 273.15 because we want these in Kelvin. 50 plus, this will be 323 Kelvin. That's definitely going to get in the way. And this one will be 278.15. Oh, sorry. There we go. Adding 273, so we get 278. Now we could start plugging things in. So we get 730 torr. Oh, I didn't plug this in. Oops. Good. Okay, so 273 torr, 20.0 liters over our 278.15 Kelvin. Scooch this equals P2, 800 torr times V2, so that's our unknown. And then our temperature is going to be 323.15 Kelvin. So we can do all of this math on the left side first and simplify things down. Do 730 times 20 divided by 278.15. So it's going to be 52.4897. This is going to be units of torr liters per Kelvin. So you notice when we do these calculations, our units multiply together just like variables would. And they cancel just like variables would too. So on the right side, I'm going to do 800 torr divided by 323.15. 323.15. So we'll get 2.4756. Again, using more numbers here than we have sig figs to avoid rounding errors. It would be torr per Kelvin now times V2. And then we'll divide both sides by our 2.4756 torr Kelvin. This divided by that. Get 21.2 liters. With what I think is the correct number of sig figs. So I want to point out too, that if we have What do I want to do this? Torr liters per Kelvin. So those are our units from here. And we divide this by torrs per Kelvin. When you divide by this, you can multiply by the inverse, and it's the same thing. So this 3 lines is the same as, although I guess it is equal to as well, torr liters per Kelvin times Kelvin over torr. So then when we do cancel these units in our final math here, we get Kelvin cancels and torr cancels to leave us with liters. So yeah. Any questions there? Cool. What is the next slide? Okay, this is just another example. I'll do that example tomorrow though. Yeah. All right, that's it for lecture.